Okay, so am I audible? Hello. So if you can see my screen and my voice is audible, kindly please either share in the chat box or just unmute yourself and speak up. My screen is visible, right? Okay, so we'll wait for just 2 to 3 more minutes and we'll start. Okay. Kindly confirm if you can see my screen and hear my voice, and be attentive in today's session. Okay, because today's session will be very important for various exams as well as for this course, because we are starting transient analysis, and this portion is very important part of electrical engineering. Okay, because it teaches you how to deal with various R, L and C networks with initial condition using a very simple analytical approach without solving any ordinary differential equation. So that part is important. So I will just request you to solve with me all the problems. Either you sit with a pen and paper and solve with me all the problems so that you remember the steps, because in these kind of problems the steps are important. And problems are easy, but if you do it using the steps, it will be of great practice and it will help you solve correctly, because there is chance of silly mistake. Okay, you can do many silly mistakes and the result may come completely reverse. So I will just request all of you to kindly be attentive and try to solve with me all the problems. Okay, I will give you time, and I will cover all the concepts so that nothing is left out, so that you learn how to analyze these kind of circuits. So welcome to the week 2 of the live interactive session, and this is of the NPTEL course Introduction to Electrical Engineering. And in today's week, we'll be actually talking about transient response. Okay, with multiple, maybe multiple L, multiple C kind of circuits, and DC circuits obviously with initial condition also. For example, the L and C, the inductor may be having some initial current, or the capacitor may be having some initial charge, initial voltage. So how to deal with those kind of circuit? And these may be multiple order, because you know that in a DC circuit, if you have two inductors, what is the order of the circuit? Anyone? Just brushing up some old concepts. So maybe I give you this circuit, okay, and ask you what is the order of the circuit?
3.
Yes. So order of the circuit will be simply the number of storage elements, right? And in electrical engineering, we have the inductor and capacitor as the storage elements, right? So number of storage elements determines the order of the system. It is nowhere related to the forcing function, right? So order is 3. And you understand that in order to solve the transient. Oh, so what you understand by transient? Can anyone just any simple analytical definition? Transient and steady state. What do you understand? When it comes and why it comes? Anyone?
Transient means sudden change in current, sir.
Yes, sudden change. Something is changing, right? But why you see such transient? Yes, it is. We are talking about signals, correct? Voltages and currents. But why they come? In which kind of systems they will come? Correct? It will come in signals, in the form of signals, or the response signals like current and voltage. You force something on your system, and some responses you see the transients. But why it
During
comes?
during
Yes.
faulty conditions, sir.
Yes, during faulty condition agreed, or some
And,
transient switching condition, switching when you are
and switch
switching.
on and off conditions.
Correct. But you will only see those transients for storage elements. Like for example, if I just give you a simple circuit with R resistance, right? See, it is also a kind of transient, but that response you will not see. That kind of response that we see, either the decaying part or the rising part in a DC circuit, I am telling, those kind of transients you will not see if there is a resistance, because the resistance neither allows any opposition or gives any preference to the change in signals across it. It neither prefers nor it retards. It neither opposes nor it encourages. It will just, you impress the signal and it will start as per Ohm's law, V equal to IR, right? So it doesn't exhibit any kind of opposition, right? As you can understand, because it is not having any capability of energy storage, right? So these kind of elements like the resistance, it will not exhibit any kind of transient phenomenon, or you will not actually observe this kind of lag or lead, because it is a slow rising means there is a lag in the response. Those kind of responses you will not observe for resistance, but for inductor and capacitor you will observe such phenomenon, right? Because of the storage element. So main thing that I want to stress upon is that the energy storage element will lead to transients in the responses, in the signals, like these kind of phenomena, right? Slow rising edge or sharp rising edge, these kind of transients in the signal you can see, and that will be determined by your system. So system containing storage elements will exhibit transients. So more of it in the mathematical form we'll just explain, we'll just define in the mathematical form also, and that will throw more light upon it. But first tell me one thing, do you know about flux and charge balance? Anyone heard about these terms? You must have heard about energy balance, right? But two fundamental concepts in electrical engineering are flux and charge balance. Anyone heard something about it can just unmute and tell what they understand about these kind of terms. Do you know about charge? I hope you know about charge. What is charge? But do you know about flux? Just unmute and let me know. Do you know about flux?
Yes, sir.
Yes, what is flux?
Number of magnetic lines passing through the middle.
Correct. So it is a mathematical parameter, right? There is nothing physical existence of such parameters, but we hypothetically form such parameters, right? And how to define it, he told correctly. That is the number of lines passing through a closed bounded surface, right? We can define flux wave. And flux may be defined for many things. It may be magnetic, it may be electrical, right? And accordingly we get non-conservative and conservative phenomena with the fluxes. So that kind of flux, what I am talking, two properties I just want to highlight in case of network theory, that the flux cannot change instantaneously. And similar with the charge is always conserved, right? Similarly, this flux, this is also can be balanced or conserved. So these two things will help us in determining some kind of voltage and current for the, actually voltage for the capacitor and current through the inductor, because we always write, right, that the current through an inductor, if I will write that IL, if you see some kind of inductor is a linear element, right? So we say that current through the inductor cannot change instantaneously, a very popular statement in electrical engineering. And the voltage across the capacitor, whatever be it, the voltage across the capacitor, so IL and VC cannot change instantaneously. Change instantaneously means, for example, current through the inductor is 1 ampere. In the next sudden transient moment or switching moment, it cannot become 1.5 ampere. So whenever you switch an inductor, the current just before switching and current just after switching will be same. And similarly, the voltage across capacitor just before switching, if it is 1 volt, just after switching, it should be 1 volt because it cannot change instantaneously. And why these concepts hold true? Because of the flux and charge balance. Because the flux through the inductor cannot change instantaneously, and similarly, the voltage across the capacitor, because the charge balance cannot change instantaneously. But these kind of statements you must have heard in your BTech or class 12 also, but they actually are not true when can anyone tell me these things always hold true or something is missing? Because you have applied Gauss law in class 12, right? While solving capacitor charge balance problems. And then you must have seen that voltage across the capacitor can change instantaneously and split. So what is the thing that we are missing? Because this statement you have also read in your class, that current through the inductor and voltage across capacitor cannot change instantaneously. But you have also solved Gauss law and charge splitting problems of the multiple capacitor, that before switching, one capacitor was charged and then another capacitor was connected, and what is the final charge? In those kind of problems, voltage change really. So what is the thing we are missing? Can anyone tell me? What is the fundamentally true statement? Yes? Someone please? Yes, you may unmute and just be interactive, okay? Just unmute and just try to participate in the discussion. You will gain more, I think. Yes, do these statements always hold true? Current through the inductor and voltage across capacitor cannot change instantaneously, obviously during switching instances. Are these statements absolutely true or something additionally need to be told before they can be applied in the problems? This will help in problem solving. So kindly just try to participate. Yes? Always true? Yes or no? I am asking.
True, sir.
Always or not?
All,
So they are not always true if the circuit's forcing function is impulsive. That is, if you apply impulsive forcing functions, then this statement will be violated. When forcing function means whatever you are applying to the inductor and capacitor. So when forcing function is impulsive, means delta t. You heard about delta t? This function, how many of you don't know? I guess all are BTech students, so you must be aware of delta t. This function, unit step function, you are aware? Ut, we write.
yes.
What is ut? How does it look? It is simply for t greater than 0, it is 1. Just a signal, simple signal, assume. So whenever time is positive, that is the time we are switching. That time will start counting. So from that time, it will be 1. But what is delta t? It is an impulsive signal. It's a very high value signal only for a small duration at t equal to 0. And its integral over time, okay, minus infinity to plus infinity, delta t dt is 1. Because it is a huge strength signal only for a small time. So when you integrate, it is 1. Like that it is defined. Okay, it can be defined like that. So only when it is a very high magnitude or high strength of signal for a very small time, because you understand, if you switch in a very small instance, the time is very small and the change is very large. The didt or dvdt, whatever duality you form, that is very high. So that is just similar to a impulse function. So when such functions, because you know what is VL, LDIDT, what is CIC, CdVdt. So these terms, when change instantly due to switching, small time, maybe di is 3 and dt is 0.00001 in microsecond. That strength is very high. So we call it impulsive. So they are delta t form. So that kind of forcing functions if you impress, then IL and VC can change instantly. Like those capacitor charge splitting problems. You charged to 100 volts of 1 microfarad. Then another capacitor came, 1 microfarad. It is completely uncharged. And you just just turn on the switch. What will happen? We'll do charge balance. Charge of this plus charge of this at 0 minus instant, just before the switching, should be equal to charge of this plus charge of this, of the total combination. So it will get that it is, we'll learn how to do this. I will again brush up how to do this. I have kept problems. So that will be just 50 volts, you can see. So that is impulsive change, right, across the capacitor. So impulsive change across the capacitor or impulsive nature of forcing function can instantly change the voltage across the capacitor. Just before the switching, it was 100 volt. Just after the switching, it will be 50 volt. But that are not normal transients, because you have a forcing function which is impulsive in nature. Why impulsive? Because the capacitor had a 100 volt charge, and immediately I force that 100 volt DC charge upon the next capacitor. So that is a impulsive change. So such kind of impulsive change in forcing function can cause immediate changes in the capacitor voltage, instantaneous changes, I can tell. So current through the inductor and the capacitor voltage can change instantly if the forcing function is impulsive in nature. When someone asks you, you can just give this example. Any problem? I have kept problem and mathematical justification also to the statement I just made now. But analytically, have you all understood? Or need some more explanation? As per these all things come as per the flux and charge balance. But this charge balance will always hold true, and flux also will change slowly, not instantly. But if it is impulsive in nature, then things can just go just change instantly, because the forcing function is impulsive. It itself is very large. So then things can change instantly. That is the simple statement. So any doubt? Because I've kept problems, so you will understand through the problems also. I hope it is analytically clear, right? So just a simple, again, another concept that I just want to tell you before I go into the modeling and the formulas. So nothing you need to memorize, okay? Just go with the concepts and then you can understand. So just tell me one thing. If the current direction is like this, then what will be the polarity of voltage for the inductor? Because current is like this, current is trying to pass through the inductor, but its general nature is to oppose the flow of current. So the property of inductance property tries to resist any change in flux through it. It means when flux is trying to rise through the inductor will try to reduce that rise in flux. But when the flux is going below, the inductor will try to raise it or maintain it. Who specified this law? This is, can you tell? This is by Lenz's law, right? This comes by Lenz's law. Anything changing should be opposed in the similar dimension. So when the current is trying to enter, just for the first time, it is trying to enter, the inductor will try to oppose it. That's why, just like a resistance, the voltage across the inductor will also try to oppose the flow of current. That's why when solving the problems, you just keep the denominations or the polarities like this. But when current is trying to fall, that is, it will, when current IL is in the same direction, but it is falling. So it is rising first. Now it is falling in amplitude, in strength. Then the polarity will aid the flow of current. Because of the simple nature of the formula across the inductor, it is actually minus L DIL dt. But we never use it in electrical engineering, this minus sign. This minus sign denotes opposing nature. What does opposing nature means? That when di dt is plus, that means it is a monotonically increasing function. When current is increasing for that instance, then the voltage will try to oppose its increase. And when does the voltage opposites increase? When it is opposite in polarity to the flow of direction of current. And when the current is trying to reduce, how can it aid the current? By just reversing the polarity. So that is the things we'll just keep on using many times in the problem. You will just get to know it. Okay. Similarly, you see that the voltage across the capacitor. Voltage across the capacitor, we can say similarly, if IC increasing, then VC will increase. It will charge, and this phenomenon is known as charging of capacitor. Similarly, this phenomenon is known as charging of inductor. Why? Because the energy stored by the inductor is also increasing. Here the energy stored is reducing. Similarly, here the energy stored is increasing. And for the next instance, if I withdraw some charge in the form of current, if I withdraw some current from this capacitor, same polarity direction, then it will you can say reduce the voltage across the capacitor, and hence energy stored by the capacitor will reduce. I hope these things are very, I think, analytical and goes with the similar analogy, right? So need not be explained multiple times. So yes. So steady state and transient response, I just explained you, maybe analytically. But can you tell me mathematically what are these? Because we are already writing na, voltage across inductor is L di dt, IC equal to C dV dt. What are these? These are differential equation, right? So once you form the differential equation with some forcing function, because you have a system, kind of black box, I told you, linear time invariant bilateral system, RLC maybe, and you apply some forcing function and you get some response for that. In between, we have the system. These are the signals, voltage or current. Similarly, here also we see the signals. And response, we are transient response, steady state response, all we are talking for these signals. But the system which is sitting in between, for which we get the response, is just a linear system, linear time invariant bilateral causal system. So we have to deal with such differential equations, and when the order of the system will increase, the number of differential equations will also increase. But the forcing function is also there. So when you write down the differential equation, I just will show you examples also. Then on the right hand side, there will be a magnitude of strength of the signal that you are forcing to that system. That is known as forcing function. For example, voltage V, that is the forcing function. So it will sit on the right hand side of the differential equation. Just I will show you also. So those kind of things you have to solve. But can you tell me mathematically, if someone of you have read, after solving those ODEs, because transient and steady state response are nothing but solution to the ODEs, right? Transient and steady state response are nothing but solution to ordinary differential equation. And solution to ordinary differential equations are split into two parts. Can anyone name them? Yes. A solution to an ordinary differential equation can be split into two parts. Have anyone heard the name complementary function and particular integral?
CF and PI.
Yes. So actually in mathematics, when you learn the solution of ODEs, you have many techniques to solve such ODEs, but we actually split it into two parts. One, the homogeneous part without the forcing function, which will lead to the complementary solution. And then one solution for the forcing function with V, which will lead to the particular integral. So I'll just show you one example. So these are some traditional methods, how you solve RL and C based networks. But it will take time because solution to ODEs take time. And it has also two parts. One time you have to make the forcing function 0 and determine the natural response, which is nothing but the complementary solution. the natural response due to the initial condition. And one solution will come for the forcing function, which is called the particular solution. Particular integral method we have. With that, we solve the forced response. So that two response is summed up to get the actual total solution of the system. So I will just write some concepts for you. So first thing is that the natural response of a system from initial conditions can be found out by without any forcing function. So it is nothing but the complementary function from the complementary function. And steady state solution, that is the forced response, you determine from the particular solution, particular integral solution. So this part we write na CF plus PI equal to solution. Solution or response you can tell. For in terms of electrical engineering we tell response, or in mathematics the solution of the ODEs, right? Now can anyone tell me which part is the transient and which part is the steady state? Or in just mathematical terms, can you tell me which part, just by seeing the response, how can you tell which part is the transient and which part is the steady state? For a DC. Yes.
CF is steady state.
CF is no, CF is the transient, right? Because the forced response, once you go to the steady state, only the forced response will be there. After the transients die out, whatever is the state of the system, that response will be only due to the forcing function. So there all the initial conditions will die out. So the forced will give you steady state, one part of it. And the transient, how can you, by seeing this solution, how can you say this part is transient, this part is, forget about CF and PI, just tell me which part can you say that this part is my transient part and this part is the steady state part, just by seeing the equation or the solution. Let's say I give you one example. Okay, solution is equal to 5 e power minus 2t plus 5. Just hypothetical one solution. Let's say inductor current. Can anyone tell me out of this part which part is the transient part and which part is the steady state part, just by seeing it?
Sir, 5 is steady state.
Correct.
And 5 to the power e minus 2t is transient.
Correct. So as you can see, this transient is comprising of the initial condition response of the system, because initially it has some value which is trying to die out, and on top of 5 you have a 5 e power minus 2t. So these two sum up, x2 and x1 of t kind of sum up to form the net xt, right? The solution. So just by seeing, when you see one part is trying to decay with time, for sure it will be the transient part. And out of that, the steady state part with time will not change, because that is the steady state strength of the response. So by seeing it also, we can just see. But mathematically, to determine these two things, we have to form the complementary function solution, and with the particular integral, we have to determine the two solutions and then sum them up. So one example of how you do that using the ODE approach, we'll only use it only for one time, just to give you motivation. But after that, we'll use the analytical method, which is much easier. You don't have to solve the ordinary differential equation. But for one time, I will solve it, just to make you realize how the complementary function, particular integral methods work, and how the solutions are determined with the initial condition, just for a first order RL circuit, right? So just see this circuit. The circuit is visible, right? Yes. Just confirm once. Yes. Okay. So just tell
Yes,
me.
sir.
So what is the order of this circuit? Yes.
Sir, 2.
Why
No,
2?
sorry, 1. Sorry, 1.
So I told you, whenever someone asks you simple question, order of circuit, right? That should be equal to number of storage elements. And I also told you that the register is not a storing element. It does not change the transient response also. It has no role to play in the transients. Just understand that from the very scratch. Whatever transient analysis we are trying to do and you are trying to learn that process, you are doing it only because of the storage elements. The storage elements are playing the nature of the dynamics and has their role in the transient response. So the forcing function plays a role in the transient response and the storage elements play a role in the transient response. And obviously the time of switching. So three things only you need to tackle. Time of switching, because accordingly you have to change the switch position and analyze the circuit. The forcing function and the number of storage elements. The storage elements basically. They determine the how the transient response will look like, because you have the governing equations for that, right? So just mathematically for one time I am solving how to solve this ODE. Can anyone help me with the KVL? Because you know VL equal to LDIL dt. Because I want to hear from you. Kindly tell me what will be the KVL. If this is I, form the KVL. So V equal to, V is gain. So I sit on this side. Gain I take as positive, for example. Then I move to that. Let's say switch is closed. Minus IR, drop. But you also know this is also drop. So whenever I know that it is a drop, so I can directly write drop LDI dt. Now V equal to LDI dt plus IR. Now the rule is to solve ordinary differential equations. First you need to, it is a first order ODE. Why first order? Because the differentiation is only done once over the I, over this variable I. So the variable is I, right? In electrical engineering, we also call it state variables. The IL and VC are known as state variables. So they are the variables upon which the ODEs are formed. Obviously, there is no capacitor. There is an inductor in this circuit. So we form the ODE with the current across the current through the inductor, right? If there was a capacitor, another equation would have formed involving the voltage across the capacitor. So the current through the inductor and the voltage across the capacitor are responsible for formation of the ODEs, and they are termed technically as the state variables, because these are the variables which are involved in the ODE. But to solve the ODE, the coefficient of the differentiation term needs to be first eliminated. So you divide by L. These are basic mathematical tools for solving ODEs. You can see that, okay? And then the rule says to multiply with what? Anyone? I think you must know the basic electrical engineering skills. You must have learned the mathematics, right? Basic mathematics part 1 or part 2. They have told you how to solve with particular integral methods, right? Because we have a forcing function and we have the natural system function. So both are there. So multiply with particular integral. What is particular integral? It is nothing but the coefficient sitting with I. Multiply both sides. E to the power integral R by L into T. We multiply both sides, right? Then what is coming? Let us see. So I go on a next page. Okay, just form a new page, okay? So I can write V by L equal to di dt plus R by L into I. And then I multiplied with e to the power integral R by L T. This is a particular integral. And how we formed it? Using the coefficient of the term sitting with I. Just why we integrated or multiplied with both sides, you will just come to know now. Okay. So this integration term will not be there. Okay. E to the power r by L into T. Integration will do after some time. Yes. So this integration is not there, right? Just e to the power r by L into T. This is the particular integral term. So can you tell me what is it coming? E to the power r by L into T into I into r by L plus e to the power r by L into T into di dt equal to e to the power r by L into T into V by L. This is coming, right? If you multiply with e to the power r by L on both sides. Everyone getting up to this? Yes, hello. Just multiply with the particular integral on both sides of this equation. Then you can see it is nothing but the differentiation of e to the power r by L into T into I. This complete term into, yes, because by chain rule, this is one part, this is one part. If you differentiate this part, then it will be r by L into e to the power r by L into T. Is coming into I. Then differentiate the second part, leave the first part. So this is nothing but this. And this second part is e to the power r by L into T by into V by L. And there is a dt also. dt, right? So do one thing. Take by splitting, you take, because there is t on this side, you take dt is on this side, right? And then you integrate. Okay. So then you integrate. Why? Because you want to find the solution I. You want to, what was the motivation? Motivation was to find the current for this switching circuit. So see, integration of this will be what? Can anyone tell me? Integration limits 0 to t, okay? Because we are dealing with causal systems. Yes, kindly tell me what will be the integration of this? You should be doing with me, right? Integration over dx, what is that? Yes, what is integration over dx? 0 to x dx. Yes? Kindly unmute and just speak up, okay? Because we'll be doing it only for one time. After that, things will become easy because we'll do it the analytical method. But this method also you need to know. It should be x, right? Yes?
E to the power of r by L by T.
Correct. Into I. You forgot the I. Whatever is sitting inside D, that will come, because integration 0 to x dx is x. So integration of d of this will be this. And what is this thing? Because v by L is constant. So integration of e to the power r by L into t by r by L. Okay. I of t I can write. So from that, I of t comes out to be plus one constant you forgot. Whenever you are integrating, one constant term will also come for the initial condition, right? Why constant term will come is the reason that C plus T, differentiation of C plus T is also 1, differentiation of T is also 1. So whenever you integrate, you always put a constant, right? And this integration limits, none of you are attentive, I can understand. Why should you put T? There will not be T. Because the limits of the integration are put for whatever is inside D. The integration term or the term getting integrated with respect to this variable dt. So the limit should be of this. So here it is okay, 0 to t, but here you cannot put limits. So for that reason, there is an additional constant that is coming. Because whenever you don't have limits, you cannot actually ignore the constant term. There is a constant term that will also come, right? So after you know this thing, can you tell me what is IT? This is a constant term, right? Just solve what is IT coming and tell me. So this e to the power of the first term will be cancelled, right? There is a e to the power r by L here also. So it will just be coming v by r. Then what will come? Yes, please solve. Okay. Plus a e to the power minus r by L into t. But we don't know a. How to determine a? Can anyone tell me? A is determined from the initial conditions, right? Because we know one thing, inductor current just before switching and just after switching, it will remain the same. Because the forcing function is not impulsive in nature. The voltage across inductor or the current through the inductor will not be impulsive in nature, right? So we can put that IL0 minus equal to 0, IL0 plus equal to 0, because current through inductor cannot change instantly. Because the current through the inductor was initially 0, it will still be 0. Because there is nothing impulsive given, right? So once you know this, you put it here. We can put IL0 equal to VIR plus A e to the power minus R by L into 0. So A is coming minus V by R. Okay, you got it. So put it back here, and I will write it with a different color. So your first order differential equation solution is coming IL equal to V by R plus minus V by R e to the power minus T by tau. Because there is a R by L into T, I write it as T by tau. So tau will be L by R. And I can take V by R common, 1 minus e to the power minus T by tau. So this is a standard equation, very popular equation of the current through the inductor for a first order RL circuit. So it looks like this. Whenever you switched on, then the current through the inductor initially will be also 0, and initially it will be 0, then it will rise up to V by R. So this is IL of T. Similarly, can anyone tell me what is the voltage across the inductor? Analytically, initially the voltage across the inductor, can anyone tell me without solving anything, what will the voltage waveform? There is a RL circuit like this. There is a switch, then a RL circuit. Okay. What will the voltage across the inductor? Can anyone tell me? One rule is for sure, that initially inductor behaves as open circuit, finally inductor behaves as short circuit. I will write all of these and make you revise once again. Just asking. Initially, inductor always behaves as open circuit because it don't allow sudden change in current. And if a element does not allow sudden change in current, and if the current has to be zero, then how will you model it? In any networks, if the current has to be zero, how you model it? Model it with an open circuit. If the voltage has to be zero, for sure you have to model it with short circuit. So inductor actually initially behaves as an open circuit. So the voltage across inductor, what will it be?
V.
Complete. Yes, V. Complete voltage will be impressed upon the inductor because it is open circuit. And the remaining part of the circuit you just analyze. No current flows, so no voltage drop across the resistor. And this complete voltage appears across this node. So the voltage across inductor is V. So if you want to draw the waveform, slowly you can see initially the voltage across inductor was V, and slowly it will be shorting itself. Because for a long time, if an inductor is connected, it behaves as a wire, simple wire. Because it does not, the current is not changing. So the inductor does not oppose any flow of current, and its voltage across it will be zero, and it will be shorted. I told you, na, if there is no change in current, voltage across inductor will be zero. If voltage across inductor is zero, we can model it with a short. So that's why generally we can write down one thing, one common rule, that initially I can write L behaves as open circuit. Similarly, initially, analogous to this, capacitor behaves as short circuit because for zero initial condition. Zero initial condition means for inductor current was zero, for capacitor voltage was zero. So if it was initially so, and I can write it like this, IL0 minus, like just before switching it was 0, or VC0 minus, just before switching it was 0, then also after switching also it will be 0. And I told you, to model a zero current you have to open circuit. To model a zero voltage you have to model zero voltage. Here you have to model zero current, because the current through the inductor just before switching and after switching cannot change, but it was 0. So how to model 0? Just after switching it will be open circuit, and capacitor behaves as short circuit. This is initially. But finally, once everything is settled, t tending to infinity, the inductor current will not change at steady state. So the voltage across inductor will be 0. Once it is 0, how to model it? Model zero voltage with short circuit. So finally, L behaves as short circuit and capacitor behaves as open circuit because it is finally charged up to its full voltage. And once it is charged up to full voltage, there will be no flow of current. Once there is no flow of current, you have to open circuit. Model zero current with open circuit. So with this philosophy, you write down what are the, you model actually. We'll see in the next slide. But tell me, what if impulse excitation is given? We have already learned, right? That what is the impulse excitation is given, both for inductor and capacitor. So let's do it once again. I apply impulse function. So what do you know? This IL of t, because VL is LDIL dt. This is I. So what will be I? 1 by L integral VL dt. And obviously 0 to t. But let us write minus infinity to t, because there may be some initial condition, some initial current through the inductor or some initial voltage across the capacitor. Actually, we write minus infinity to t only. But if nothing is there in the initial, then we neglect that and write 0 to t. But now tell me, if voltage is impulsive, what will happen? Yes, tell me. Minus infinity to 0 minus, just before switching, VL dt, plus 0 minus to 0 plus, in between that time, VL dt. I am breaking it, okay? 0 plus to t, VL dt. Now if VL is delta t, then what is integration 0 minus to 0 plus delta t dt? I told you it is 1. It is by definition of impulse function. So it will be 1 by L, this part. This part will be 1 by L because this is 1. This part will be what? Can anyone tell me? Assuming 0 initial condition.
0.
Yes. This part will completely go to 0. Because the initial current, this is nothing but initial current. Integral minus infinity to 0 minus. Initial current just before switching. So there was no initial current, so 0. But this was impulse, so 1 by L, because this integration is 1. Plus this what you can tell, 0 plus to t.
0.
No, not 0, but how can you say 0? Because you cannot say what is the forcing function you need to know. But the forcing function is delta, right? It should be
Delta.
I 0 plus. It should be specified, okay? So if I write I 0 plus, then this should be 0. Because integration of 0 plus to 0 plus will be 0, right? But if it was not IL of 0 plus, then it would have been the function, right? Whatever is the function. But that function was also 0. So it will be 0 in any case, right? So that's, you are correct. So 1 by L, right? But you can see I of 0 minus is 0. But I of 0 plus is 1 by L, something different. But I told you, if impulse, then it can change. So you just saw that current through inductor can change instantly if forcing function is impulsive. We saw the proof also. Similarly, for capacitor, you can do similarly and you can see. So you can also see one more thing, energy stored before just switching. So 0 minus, I am denoting 0 minus for before switching. Obviously 0 for switching instance. T is equal to 0 means the time of switching. And 0 plus means after switching. So please make yourself comfortable with these notations, because now we'll dive into the main analytical method, right? And solve the problems. So energy stored before switching is not equal to energy stored after switching, because what is the energy? Half Li square. But I before switching and after switching are coming different because of the impulse forcing function. So that's why the inductor energy is changing just before and after switching because of the impulsive excitation. That is what I wanted to tell you. So we saw that the first order ODE solution we derived, but it was hectic process, right? A lengthy process. So in order to simplify things for the DC, we build out the analytical approach. So the analytical approach is simple. It gives you a formula that the response, this is the response, right? Whatever response you want to determine, the current through the inductor or the voltage across the capacitor, you can determine it. Simply, it is equal to the final value plus initial minus final value into e to the power minus t by tau. Tau is the time constant of the circuit. And this formula only holds true for DC circuits. Only for RLC, only involving RLC elements. So it saves time. It don't need to solve the OD. For the DC problems, you can just in 3 steps write down the expression of all the parameters: voltage across the inductor, current through the inductor, voltage across the resistor, current through the resistor, voltage across the capacitor, current through the capacitor. All these things you can write in one line by following 3 simple steps. So that 3 simple steps you need to follow. What 3 simple steps? 0 minus, 0, 0 plus. Obviously 0 you don't analyze. 0 minus 0 plus and infinity. That is at steady state. The steady state behavior you need to analyze. Plug in the value here. The 0 plus means after switching instance you analyze, plug in the value here, and then you get the final value. Because 0 minus and 0 plus for any inductor or capacitor, things will not change instantly because we don't have a always similar analogy. But why we need to do 3 steps? Can anyone tell me? 0 minus and 0 plus, both steps we need to do. Why? Because of the initial condition. Initial condition always determined from first step. That is 0 minus. Before switching, what was the circuit? If you don't see the circuit structure before switching, how will you know the initial current or initial voltage? Now, once you solve that initial circuit before switching, you know the initial current or initial voltage. With that information, you again go back to the 0 plus after switching instance circuit. So step 1, formula looks easy, but the 3 steps also needs to be followed correctly. Step 1, 0 minus. Initial behavior of the circuit. You draw the circuit, 0 minus, and analyze. And plug in the parameter values here. Then step 2. Step 2, t equal to 0 plus. What is the behavior? What is the circuit structure after connection? Because after connection, after the switch position is shifting, the circuit structure will change. So 0 plus you need to see. Then step 3, t equal to 0, t equal to infinity. Final steady state value. Because you need these values, f0, f infinity. So these are the 3 simple steps of the analytical method. With that, you can easily determine any response, right? For one voltage, you can determine one current. For another current, you can determine voltage. For across VR, voltage across resistor, current across resistor, voltage across inductor, current across inductor, or DC, IC. Anything you can plug in here, this side. Anything you can actually derive for the response, right? So this holds for only RLC and DC networks. Now, how to model the initial conditions? That is very important. One question still remains unanswered before attempting all the problems involving the transient analysis. That how to tackle the initial conditions, how to model actually. One thing I already told you. One very useful information. So in this page, we'll write down all these things, right? Which will help you solve the problem. So model 0 voltage with anyone? Model 0 voltage with open circuit or short circuit?
Short.
Yes, always. Model 0 current with open. Simple 2 rules, right? Now you come here. How to model the initial condition? For example, just we'll show you 2 examples and you will understand. Okay. So this was a capacitor. It was an inductor. Now it was having some 1 ampere as initial current. Now it was having 1 volt as initial voltage. Now while solving transient problems, at t equal to 0 plus, just after switching, how to model the inductor and capacitor? How to model? Because t equal to 0 minus will help you find out what was the value of the initial parameters, initial current or initial voltage. T equal to 0 minus, why? To know value of IL 0 minus or VC 0 minus. These things it will tell you. If I ask you, who will tell you the initial condition? You have to go back to the circuit, analyze it just before switching. I will draw the switch and you can see what connected where. So just before switching instance, you have to analyze the circuit, look at it properly, and apply your concept that inductor behaves as short circuit in steady state and capacitor behaves as open circuit in steady state. So L behaves as short circuit in steady state. Why I already told you sometime before that dIdt is 0. That's why. C behaves as open circuit. dVdt is 0. I0. IC 0. So behaves as open circuit in steady state. Using these four analogies, you need to form the circuit and see what was the current through the inductor in the initial condition. Now, once you know that, let's say its value is 1 ampere. So how to model it at t equal to 0 plus? That is the question. So what we do, model initial currents in shunt means in parallel to inductor with open circuit. Why open circuit at t equal to 0 plus? Because inductor does not allow sudden change in current. So if IL0 was 0, IL0 minus was 0, IL0 plus would have been 0. But IL0 minus is now 1 ampere. So IL0 plus is what? Is nothing but, here need to model, because voltage across the inductor can change instantly, but current cannot change instantly. So, but we need the voltage across the inductor in the t equal to 0 plus step, which is the step 2. So, in order to find that, you already know that voltage across current source can vary instantly. Similarly, voltage across inductor can also vary instantly. So, in order to find that, what we do, we apply the initial part in shunt, the inductor. So, you model it with a current source, and its value is 1 ampere. Because I already told you that 0 current means open circuit. 0 ampere current can be modeled with open circuit. So we did open circuit. This part is the zero initial condition assumption, but zero initial condition is not there because initially 1 ampere was there. So connect it in shunt. This is the modeling rule. Now for the capacitor, what you will do, model C with initial voltage. How? As a voltage source of initial strength in series with capacitor. But what is capacitor as in zero initial condition? 0 volts. So how to model 0 volt? With short. You are understanding why I'm doing like this? Because assuming zero initial condition, how a capacitor will behave? Initial capacitor voltage was 0. So once you switch on, the final capacitor voltage also should be 0, because voltage across capacitor cannot change instantly. And if voltage across capacitor needs to be 0, how to model it? How to model 0 voltage? With a short circuit. So I do that. Polarity should be according to the polarity of across the capacitor, right? If the polarity is like this, so the voltage polarity of the initial voltage source should be like this. If it is opposite, it should be opposite. Then you need to draw capacitor, but it will behave as a short, because voltage across it is 0. And to model voltage across a capacitor as 0, we need to short. So this is the model at t equal to 0 plus. At t equal to infinity, inductor will behave as what? Open or short? Yes. Yes. You short the inductor. It is simple wire, right? Inductor is a turn off wire. Remember like this. And capacitor is 2 plates. It is open, right? DC is open. Capacitor is open and then inductor is short. Remember like that. Only part where you need to be focused is the t equal to 0 plus part. After you know the initial condition. The t equal to 0 plus, you need to model with the initial condition. Don't forget about the initial condition. Maybe you forgot this current source. Then circuit analysis will change and your answer will come different, which is wrong. Because if the initial condition is there, you need to include those sources as the initial source strength, right? Now we come to the problems, right? If you understood all of this, you can solve all transient problems in DC. Now, so we'll do maybe 8 to 9 problems and you'll cover all the concepts. So see the first problem. First problem only, it will take some time to explain you. After that, I will do directly. I will write direct steps, and you can also write direct steps. So let's start very quickly. You write like this, step 1, at t equal to 0 minus. What is that? See, switch has been in position 1. It is already telling you. So position 1, drop 10 volts. Let's assume this is 10 volts. Now assume R to be 1 ohm, L to be 1 milli. 1 Henry directly you assume, okay. So how will it look like? 10 ampere, right? 10 ampere because the inductor was connected for a long time and will behave to be a short. So IL0 minus initial condition is 10 ampere. Anyone having any doubt in this step? Tell me. The problem says that the switch was connected at position 1 for a long time. What does that mean? That circuit has already reached its steady state. And its steady state, the inductor behaves as a short. Then simple Ohm's law to calculate the current through the inductor at initial condition t equal to 0 minus. It was 10 ampere. Now can you tell me, calculate everything. Whatever elements are there, calculate their voltages. VL0 minus, what is it? Short. Correct. VL0 plus, what is it? Sorry, nothing 0 plus. Now we are doing with 0 minus. So VR0 minus, what is it? Just before switching. It is nothing. It will take the complete voltage drop. 10, yes. Complete voltage drop taken. Now you come to, by having this information, now you come to t equal to 0 plus. This is very important information that the analysis gave you, because you now know the initial condition for the current through the inductor, which you will embed in the next model, which is at step 2. At step 2, why important? Because the switch position has changed. The circuit nature has now changed. Where the switch position went? To 2. So draw it. Draw everything, okay? Now, can you tell me? In this condition, inductor is having some charge. What is that? Inductor is having some energy, I can tell, not charge. Likewise, people tell inductor is charged, but inductor doesn't store charge but magnetic energy, right? So inductor is energized with 10 ampere flowing in this direction. Flowing in this direction. But inductor does not allow sudden change in current. So the current will be in 10 ampere, right? Current cannot change instantaneously. However, the inductor polarity will reverse to allow the aid the direction of current. But we'll not remember this. This will automatically come. How you just see. What I told you, that once you change the switch position, you need to model the inductor as a current source in parallel with open circuit. Right? So I did that. Why open circuit? Because current through the inductor, assuming zero initial condition, should have been 0. So open circuit. Model a 0 current with open circuit. But it does not have 0. It had 10 ampere. So I modeled it with parallel. This is the technique which we use for modeling initial condition for the inductor. Assuming 0 initial condition, inductor would have behaved like open circuit because it would have been 0. But now it is not 0, so connect a parallel current source, 10 ampere. The current source direction should always be in the direction of the current which you assume. And obviously, why we assume current in this direction? Because 10 volts lead, positive lead is connected at that side. So current direction we assume true. Because direction also is important, right? Direction will not tell you. It will tell you the strength. Direction you need to analyze by your philosophy. Positive lead to negative lead, that's why. So now you tell me, what is IL0 plus? 10. What is VL0 minus? Just you see the magic it will happen.
10.
Is it 10 or something else? You see, this is VL, for example, if I assume. Then what is coming?
20.
Apply KVL, okay. So in KVL, I have to assume some direction. So drop I am assuming positive, okay. 10 into 1 drop. and this is again drop, right? Like this I am moving in the loop. So 1 into 10 drop. Then again this is drop, right? Because VL I assume to be like this. But now VL, it is telling me automatically that VL should be minus 10. The thing that I wanted to tell you here, that inductor, to maintain the same current, actually reverses its polarity. And that's why this problem automatically gave me minus 10 volt. You see the beauty of this step? These steps are beautiful because they automatically give you the direction if you understand properly and do properly. So it is automatically telling you mathematically that the voltage across inductor is reversed, right? Voltage across inductor is reversed. It is automatically telling you without doing anything, without just by just writing the mathematics, by just writing the KVL loop equation, you can say that the voltage across inductor has reversed. Why? To maintain the same current. This is the thing that it is telling you, right? Just I also explained you using a different philosophy using Lenz's law. This is just example of Lenz's law. If current is trying to increase in the switching instance, then voltage will opposite. But if current is trying to reduce, then voltage will aid it. Here you see the voltage across inductor is aiding the flow of current because inductor is trying to discharge. When the inductor is trying to discharge through the resistor, what will happen? The current through the inductor will try to reduce because it is dissipating energy through the resistor. The stored energy inside the inductor is dissipated in the resistor. So in order to resist that, because the current is trying to fall, the voltage polarity across the inductor is reversed to aid the flow of current. So this is what actually this infers to. The negative sign actually infers to the reversal and the polarity of the inductor voltage to aid the current. So this is how the mechanism is going on inside the circuit. This is how everything is going on. So you know how T equal to 0 plus, you know. So this is minus 10 volt. Don't ignore the negative sign here, okay? Because you already assumed one direction. VL, I already assumed one direction. Don't change it throughout the problem. Keep it same. And circuit will automatically give you the sign of the voltage polarity, okay? If you change it, it will not come. Then it will come. You have to take that direction. If I already know that inductor is changing polarity, then again I don't need to embed here, right? Because I have to take this as the final direction, right? So either way you can do. Now at t equal to last step, infinity. T equal to infinity, I told you how to model. Inductor will behave as short. So it is just simple, a shorted inductor. But voltage direction, you assume whatever you assumed initially. So VL infinity is 0. VR infinity is what? 0. IL infinity, because it is a series connection, all are 0. Now you see how you can write everything. So I may ask you VL as a function of time for this circuit. You can answer it. Also, I may ask you VR as a function of time. You can answer it. IL as a function of time or IR as a function. Everything you can answer. Now let me ask you only IL. Can you tell me what is IL? First answer this. Then you may answer what is VL. Yes. And IR also you can answer, right? Everything you can answer. So IL you can tell first. What is it? According to the formula. IL infinity plus IL 0 minus IL infinity e to the power minus t by tau. What is tau? L by R. What is L? L is, let's say 1 and 1. So tau is 1, right? So now tau is 1. So you calculate this. IL infinity is what? 0. Plus IL 0 minus or IL 0, both are same. So 10 minus 0, because initial condition is a final condition, IL infinity is 0, e to the power minus t. Tau is 1, so we neglect. So 10 into e to the power minus t. So if I draw the waveform IL of t versus t, then it will be simply a decaying waveform with strength 10. So what is it telling you? The inductor is discharging. And the inference also goes similar. That first the inductor was charged completely at position 1. After that, at position 2, it is dissipating the energy stored. starting from t equal to 0 plus, the inductor is starting to dissipate the energy through the resistor. And the dissipation always implies a decaying waveform, exponentially decaying waveform for a first order RL circuit, as we also saw the solution in the ODE. Anyone having any doubt in this? So it is matching. You can also check for DC circuits. You can just see whether the inferences are matching. Just see the inductor is charging, you can see, and then once the switch position change, inductor is discharging. That is the general inference, which you can see without writing any equation. And things should be like this. Once we start solving more problems, the things will become easier. So now tell me, what is IR of VL of t? Tell me. Similar, VL infinity, VL0 minus VL infinity e to the power minus t by tau. Tau is 1. Now what is VL infinity? VL infinity is 0. VL0 is what? VL0 is 0. Yes. So VL0 is what? Sorry, 0 plus. This will be 0 plus, right? So VL0 plus is 10 with a minus sign. And this is e to the power minus t by tau. So as you can see, this voltage is also. So this formula actually tells you 0 plus after the switching instance what is happening. So take the 0 plus, right? This one, because this is 0. So it is not bothered about that because we are doing the transient analysis after the switching state. What will be t greater than 0, right? Because 0, we already know what was happening at 0. So what was t greater than 0? The analysis. So 0 plus you tell. So 0 plus should be minus 10. Huh? So then the inductor is shorting itself at the steady state, like this. So these things you can just see. Okay, these are very easy. So let us do the next problem. I think similar kind of problem we have already done. Only a voltage source is happening here. So if you want to do, you can do. You can just solve this problem also. So I will give you maybe 1 or 2 minutes and you solve this. Okay. You tell me, solve in 3 parts at t equal to 0 minus y to determine initial condition. And then step 2 is t equal to 0 plus, modeling the initial conditions. Modeling initial condition with new circuit. Why new circuit? Because switch position has changed. With new circuit with shifted switch, right? And then third step is final steady state circuit analysis. Why 3 things we need? Because for the formula we need 3 things, right? Initial condition we need, and then these 2. So analyze everything, you should draw and then determine. Okay. So for 3 things actually, IL, VL and VR, you determine. So whenever you do step 1, you should always determine IL0 minus, VL0 minus and VR0 minus. Step 2, you should determine IL0 plus, VL0 plus and VR0 plus. Step 3, you should always determine all the 3 parameters that are being asked: IL infinity, VL infinity, VR infinity. So try to determine all the 3 values, and you should draw the 3 circuits for the three actually steps, because the circuits are changing, because you need to replace and maybe model with different initial conditions. So draw and do this problem yourself. Okay, I will wait. I will give you 2 minutes and you solve and tell me. I will ask you. Okay, you need to tell me. Yes. Simple. Okay, first assume initial condition switch at position 1. So draw switch with position 1, draw the circuit at steady state, analyze what will be 0 minus, and then t equal to 0 plus. I told you how to model the initial condition with charged L and C, and then again redraw the circuit with the new shifted switch position and try to determine the parameter strengths at 0 plus. Then once you determine that, then you go to t equal to infinity, and that 0 plus and infinity values you put in the equation, in the formula, that is f of t equal to f of infinity plus f of 0, okay, minus f of infinity into e to the power minus t by tau. Tau is L by R for RL circuits and RC for RC circuits. And for multiple N and multiple C, L equivalent and R equivalent. Similarly, this will be R equivalent and C equivalent. See, some problems are also there. So don't be afraid. All kinds of problems and concepts are being solved. Now need just to be participating, and then you'll be able to solve everything accordingly. So draw the 3 circuits maybe, and then try to determine and tell me. Okay, I'll wait. I give you 1 to 2 minutes, and it will not take more than 1 to 2 minutes. Okay, just 3 circuits you draw, and you will be able to answer all the questions. Okay, this will be now not taking more than 2 minutes each problem. So everyone's solving, right? I just want to confirm that everyone is solving. So I give you 1 minute, okay, 1 to 2 minutes. I want all of you to solve, okay? Kindly solve so that it can help you. These problems will help you in solving all the exam questions, different exam questions, as well as many this course assignments and exam problems. So it will be helpful. So I want all of you to solve yourself first. Then only you will understand all the steps. By seeing only you will not understand all the steps. Unless and until you solve each problem yourself, it will be of no help. You will not be able to do a single problem in the exam if you don't solve yourself. So I suggest all of you please solve this problem and tell me what I need to do. I will just listen from you and write, so that you first solve and then tell me. Okay, you take 1 minute and then try to solve the problem. Okay. Done. Anyone wants to tell me how to write t equal to 0 minus? Please, I want to hear one from you and another from another person like this. So what is IL 0 minus? How will an inductor behave when it is connected to an ideal DC voltage source for a long time? Yes, it is for a long time, right? Like this. So how will the inductor behave? At t equal to 0 minus, I am telling.
V by R.
Correct. So it will short. So how to write IL 0 minus? It is V by R. Now you tell me what is VL 0 minus and VR 0 minus. If inductor is shorted at this moment, it is 0 volts, and VR is complete node voltage appears across this R. So now we do first step is done, correct. Now next step, You know that current through the inductor is V by R. Now draw the new circuit with the modeled initial condition. Can anyone tell me how do I draw new circuit? Because switch position has shifted to 2, circuit has changed, but I need to also embed the initial condition. So how to draw? Can anyone tell me? Switch position at 2 means V2, but inductor needs to be modeled with 0 initial condition plus initial condition. Initial condition is a current like this, which is of strength V by R, but I need to open circuit because inductor with 0 initial condition should not have any current, but it has current. So open circuit with shunt with parallel with V by R. So now you tell me what is VL 0 plus, VR 0 plus, and maybe IL 0 plus. IL 0 plus is V by R, correct? And VL 0 plus and VR 0 plus. Acha, don't confuse. Many of you might tell, I have open circuited. How current comes V by R? I have not open circuited the inductor. I have modeled it like this. Current through the inductor still remains V by R. I only modeled to analyze the voltage across the inductor. Okay, to find the voltage across the inductor, I did this at t equal to 0 plus. Don't confuse that no current will flow. Current will flow. This is the complete inductor model, this part. So don't confuse with 0, right? So VL 0 plus, to determine it, I modeled the inductor with initial condition. So now you tell me how to VL 0 plus. What is VL 0 plus? V2 KVL, apply KVL, minus current, V by R current is flowing into R. Sorry, V1 by R hoga na. This is V1. So V2 minus V1. Anybody has any doubt in this step? Tell me. Hello. Yes, hello. Are you doing? I am not hearing any response. If it is so, then I will stop the session if I am not getting response. All of you should unmute and at least participate in the discussion, right? So please tell me what is the answer you are getting or not. If you have any doubts, then unmute and speak yourself, okay? I want to hear answers. So tell me, one of you, what is VR 0 plus? Yes, I want to hear answers. What is VR 0 plus? That is this one. Tell me. Current into resistance. Voltage across resistance. What is current? V1 by R. Resistance is R. So V1. Everyone getting or not? Yes or no? VL I wrote, VR I wrote, I wrote at 0 plus. Then what is the last step? Last step is to find out a steady state. So steady state, what will happen? Inductor will short itself. Current will be like this, V2. What will be it? I of infinity. What will be it? V2 by R. What will the voltage across inductor at infinity? It will be 0 because it is shorted. Why shorted? Because at steady state inductor behaves as short circuit. What is voltage across resistor at infinity? It will be V2. So all equations now we have derived, and now we are ready to write IL of t. So now one of you just tell me the expression of IL of t and VR of t. Two things you tell me from these things. Yes, complete equation I want to hear from two of you. IL of t and VR of t. You all know that IL of t is IL infinity plus IL 0 plus minus IL infinity whole into e to the power minus t by tau, where tau is nothing but L by R. Okay, L by R we already know. For simplicity, assume L to be 1 Henry, R to be 1 ohm. Okay, simplicity. Now VR is VR infinity plus VR 0 plus infinity as per the equation, and then it is minus t by tau. So plug in the values. What is it coming? Tell me. Yes, tell me.
Sir, VL0 plus is V1 minus V2.
Which one you are telling me?
Second one.
Second one, okay. Second one, VR infinity, how much? Let's see. V2.
VL0 plus.
Yes, V2 ना? VL नहीं है, ये V2 है, ठीक है?
नहीं sir, वो at t is equal to 0. Second, VL0 plus.
Yes, VL is what you see. VL0 plus is V2 minus. हाँ, आप कोई डाउट पूछ रहे, समझ गया, मैं समझ गया.
Yes.
आप हाँ, तो ये
V1 minus V2 होता है ना.
Okay, V2 ये है, ठीक है? I am writing like this. Okay, you apply KVL. Let's see, ठीक है? V2 गेन को मैं पॉजिटिव ले रहा हूँ, ठीक है? तो गेन माइनस करंट ऐसे आ रहा है, माइनस ड्रॉप 1/R into R माइनस VL भी तो ड्रॉप है, इक्वल टू 0.
Okay.
So VL is V2 minus 1. Whenever you have doubt, you just write KVL. That KVL to the direction. But one thing, when you have assumed one direction at the start of the problem, don't change it. That's why you should be experienced enough to choose the correct direction, right? Now, how you choose the direction? By seeing the positive lead and assume as drops. If it is not drop, then it will give you the negative of that, and you will go ahead with that. It will automatically give you that sign. So don't change the convention. You keep writing, the mathematics will actually tell you the answer. So now you see VR infinity is what? VR infinity is V2. Now VR0 plus is V1. Okay, minus VR infinity is what? V2 into e to the power minus t by tau. Tau is 1 for simplicity. So what is the answer? V2 plus V1 minus V2 e to the power minus t. This is the response of the VR. Now what is IL? Tell me, anyone. Tell me what is IL? IL infinity is what? Yes, IL infinity is what? I already wrote IL infinity. See this circuit. See this circuit. What is IL infinity? Easy, right? One voltage source and one resistance. What is that? V2 by R plus IL0 plus kitna hai? V by R, V1 by I, sorry, V1 by R, sorry. V1 by R minus V2 by R into e to the power minus t. I hope you can see it clearly. Whatever I am writing, V2 by R is the initial current, is the final current, right? IL infinity. This is IL0 and this is IL infinity. Any doubt? Tell me. Any doubt in this step? Tell me. I hope it is clear, right? It is easy. Only 3 circuits you solve and then you write. Similarly, you solve the next problem. The capacitor now. And then we'll jump to advanced problems, right? So do quickly. It should not take more than 2 minutes now. Anything, you can just determine VC, IC, VR. So you maybe do 2 and split into 3 parts. T equal to 0 plus, T equal to infinity, and T equal to 0 minus for the initial condition. Then model is the initial condition and then the final steady state part. So now what you tell, you can. So let us do. I will give you maybe some 1 minute to try and then we'll do. These are first order circuit, right? It should not take more time. So what is it? VC, VR. So VC is 0. VC 0 minus is 0 because now it is not connected to the source. You can direct that 0 minus is 0. IC 0 minus is 0. Now you connect and draw the circuit with the zero initial condition assumption, which will give you how does a capacitor behave when it is just connected, like a short, because the initial voltage across the capacitor was 0. Now to model a 0 voltage, you need to short. Okay, so now this was the capacitor. Now it is short. It's a model, right? It is modeled as short. Okay, so now what is VC0 plus? It is also 0. What is VR0 plus? Complete node voltage appears. And then IC0 plus?
V by R.
So you saw current through capacitor can change instantly. Just like voltage across inductor. Now you see what is infinity at what circuit behavior. Capacitor will open itself up because it is now completely charged. So what is now VC? VC is now V. VR is now 0. At infinity, I am telling. But I of C is now at infinity. It is completely charged to the voltage. So no charge flows and hence no current flows. So all are 0. So now tell me all the things. VC, IC, VR. VC is written as VC infinity, which is nothing but volts V plus 0 minus final e to the power minus t by RC, which is nothing but V into 1 minus e to the power minus t by RC. Is it intuitive? With time tending to infinity, the capacitor should be fully charged. So voltage should be increasing like this from 0 to voltage V. Let's see. Yes, it is matching. E to the power minus infinity is 0. So it will be matching, right? Just check like this, cross check. So now IC of infinity is 0 plus initial. So final minus initial is V by R minus final e to the power minus t by RC. So current should reduce. It is reducing. Voltage increasing, current reducing of the capacitor. Now voltage across capacitor is increasing. So voltage across resistor should reduce. Is it coming? Let us see. VR is nothing but VR infinity, which is 0 plus VR0. VR0 is V minus VR infinity to the power minus t by RC. So yes, voltage across resistor is actually reducing. It should, because the capacitor voltage is rising, and to maintain the KVL loop, it is reducing its voltage, which is natural because the current through the circuit is reducing because of the capacitor charging itself, and hence the voltage drop across the resistor is also reducing with time. So accordingly, it is coming, right? I hope this was very easy problem, right? Similar one problem is there with the changing position. I think you can do it as a homework because it is very easy. You just write 3 equations and it will come, right? So there is a summary which I want to write for you before going to the 3 advanced problems. So 3 more advanced problems we'll do just to clear your concept so that you can tackle all kind of problems. But before that, I want to just write a summary for you. Okay. So you may also take this summary down, which includes all the things we have just discussed, which will help you to solve the problems. So take this down with me. Okay. I hope all of you are with me, or someone is lagging behind or having any doubts. Till now, all are with me. So kindly raise your hand or just give an affirmation so that I can proceed. Yes. Hello.
Yes, sir.
Yes. So I will write down. Okay. Take down with me. So I want to write a summary. Okay. Just all the things we have discussed in a single page for problem solving purpose. Okay. Okay. So what we actually are doing, I am just writing that thing down so that you never forget what we discussed. So t equal to 0 minus, we were having 2 opportunities, with source or without source, right? Just write it down in a copy, okay? And similarly at t equal to 0 plus, we were having similar opportunity, I will write that on top only. Next, let me write t equal to 0 minus 0 plus and infinity. 3 steps we were following. With source, without source. All type of problems can come. Any of the 3 circuits, it may have with source or without source. So what we were doing is, with source, we were just in replacing at t equal to 0 minus, I was replacing L with short circuit because it has reached steady state. Find initial current, because t equal to 0 minus is for initial condition determination. Find initial current, and then at t equal to 0 plus, you model current source in parallel with open circuit. That is what we were doing, right? For C, what we were doing with source, C replace first with, because with source means it was something like this. So capacitor would have reached its steady state. So with open circuit, because it has reached its steady state, so capacitor would behave like open circuit, not charge further. And then what we will do, find the initial condition, and at t equal to 0 plus, model as a voltage source series with zero initial condition means short, because it is 0 volts. So without source, if you find something, then L is relaxed, right? L is relaxed to discharge, because there is no charging, because in absence of a source. So what will the energy storage elements do? If you have a charged energy storage element without any forcing function or any source, and you connect a resistor, it will dissipate all the energy. Similarly, C is relaxed to dissipate through R. Itself cannot dissipate, so it will dissipate through R by flowing the current. Okay. Now, similarly with source at t equal to infinity, steady state, L is short circuited, C is open circuited. Similarly, without source, L loses its energy, C loses its energy. Similar analogy. But at t equal to 0 minus, if it is without any source, then IL 0 minus would have been 0. So IL 0 plus would have been 0. How will you model IL 0 plus? Or VC 0 minus equal to 0, VC 0 plus equal to 0, because the initial circuit was not without any source. So all would have discharged by then. Then at t equal to 0 plus, it would have also been 0. So it can just imply open circuit, and it can just imply short circuit. At t equal to 0 plus, I am telling, if the initial part at t equal to 0 minus was without any source. If without any source, all the storing elements would have already dissipated. So at t equal to 0 plus, they would have just can be replaced by their short and open. Okay. For inductor, you need to open because no current was flowing. So no current modeled as open circuit. For capacitor, initially it was discharged, 0 voltage. So 0 voltage you can model with short circuit. So always remember. Why short circuit? So to model 0 voltage. Here open circuit to model 0 current. So this was the summary, just I wanted to just highlight. Now we go to the 3 advanced problems that I have kept. Advanced means nothing but a more number of solutions you need to do just to actually tackle such problems with multiple L and C. Just that. So that you can do all kind of problems. I just want to ensure. So advanced problem number 1 is asking you, it has multiple L and C, just that. And it is asking you to determine these parameters. If you determine these parameters, then what you can just write the equation for the responses for IL and IL1 and IL2. And similarly also for VC, right? VC, I can say 1. So, or VC, just simply VC, because there is one capacitor of T. Yes, so you kindly solve the problem. So since we don't have more time, or you will just solve the problem, start solving. So at T equal to 0 minus, how you can solve? It's just been an open circuit, right? And 1 Henry and then 1 micro, 2 ohm and 2 Henry. But this circuit is without any sources. So all the currents at initial would have been 0. Voltage across capacitor would have been 0. And now we move to the T equal to 0 plus. At T equal to 0 plus, inductor can be, since inductor is not bearing any current, has no initial condition, so inductor can be shorted, since it is, open circuited. Why open circuited? Because always remember that we model 0 current with an open circuit and 0 voltage with short circuit. Since inductor was not having any initial current, we model 0 current as open circuit. And capacitor will behave as a what? Short circuit. So your VL1 and this is VC. Similarly here VL1 and VL2. Now at 0 minus we did not determine. 0 minus के लिए भी कर लेते हैं. 0 VL1 0 minus and VL2 0 minus. ये क्या होगा? VL1 0 minus is 0 volt. 0 volt सब 0 होगा. ठीक है. Okay. Now you determine what will it take. Inductor open circuit. Okay. VL2. This is 1 ohm. This is 2 ohm. Yes. So tell me what is the current? This current IL1. IL1 0 plus. Yes. 0, right? And IL2 0 plus is also 0. And since the capacitor is shorted, VC 0 plus is also 0. Then determine what will be the final T equal to infinity, at T tending to infinity. Inductor is replaced by, at T tending to infinity, inductor is replaced by what? Short circuit. And capacitor is replaced by open circuit. So inductor will actually behave like a short. Okay. And capacitor I open. So what is capacitor voltage? VC. Inductor voltage has all gone to 0 at infinity. And what about the currents? Yes. What is IL infinity, because IL infinity and I2 infinity are both same, right? IL1 infinity equal to IL2 infinity, I write. And what is that? This is 1 ohm, this is 2 ohm. So 1 by 3. 1 by 3 ampere, right? And this voltage, you tell me, what is this voltage? VC equal to 1 minus this current into 1. So 2 by 3 volts. Okay. VC infinity, I am telling this one. So accordingly, you can write. Okay. Easy, right? Only the node equations. You understood why this is coming? Because this is the current flowing 1 by 3 ampere. So 1 by 3 into 1 drop from 1 volts gives us 2 by 3 volt across the capacitor. Solve the next problem. I give you 1 minute to think and then do it. Okay. Okay. Yes. What to do? T equal to 0. Connect at the initial position and check the circuit for determining initial conditions, right? So one thing to note is that switch position was like this. So how can I model the inductor and capacitor? VC 0 minus would have been 0, and this inductor would be short, behaving like short at steady state. So VL 0 minus will also be like 0. And one thing is the current, which is IL 0 minus, to determine the initial condition 2 plus 3, so 2 amps. Now come to T equal to 0 plus. T equal to 0 plus, we need to embed the initial conditions with the model. So now shift new switch position and redraw the circuit with the shifted position. 2 ohm, 3 ohm, and this is the place where you need to insert the inductor model, and this is the capacitor. But capacitor was having initial voltage as 0. So now to model the capacitor, it would behave as short, because the process of modeling a 0 voltage is 0 by short circuit. Model 0 voltage as short circuit. Now this is VL 0 plus, which is to be modeled with the current in this direction, which is nothing but 2 amps and a open circuit, which will give me VL0 plus. Now to determine VL0 plus, you have to see the circuit which is forcing. Actually, let me do with another color. So 2 amps current source is connected in this branch. So this is 2 ampere, but there is a loop existing here. So can you tell me the current flowing in this loop, outer loop? 10 by 2, 5 ampere. So the current pushed from the source is 5 ampere, and it is splitting here as 2 and going as 3 here, and then returning as 3 here, but coming as 2 here and merging with this point to become 5 here. So now to determine VL0 plus, form the KVL within this small loop to determine 10 volt minus, this is how much ampere? 5 ampere. 5 into 2 ohm drop. So this is, and then minus drop again 2 ampere into 3, then again a drop of VL 0 plus equal to 0. This is the KVL equation that I am writing. So 10 volt was the gain, then a drop of 5 into 2, then see this loop, then a drop of 3 into 2, then a drop of, because current source is there, so the voltage across it we assume to be VL0 plus. So according with the sign convention, I'm dropping. So minus. Now you see what is VL0 plus, take it on the other side. So 10 minus 10 goes off. So minus 6 volts. So VL0 plus is minus 6 volts. So now you have asked DIL dt. So L DIL dt at 0 plus equal to 6 with a minus sign. So what is DIL dt with a DIL 0 plus dt? Minus 6 by 2. So minus 3. DIL dt with 0 plus is nothing but 3, minus 3. Got it? Because voltage across inductor is nothing but, at that moment is nothing but current differentiation with a L multiplied with a L. Similarly, do for the capacitor, that what is VC0 plus or IC0 plus, you tell me. IC0 plus is 3 ampere, right? You can see here. This is IC. Now VC0 plus is 0 volts. Got it, right? And IL is 0 plus is 2 ampere. Now the final circuit. Let me do with another color. Final circuit looks how? How the final circuit will look? 10 volt, 2 ohm, this is 3 ohm, but the inductor is now shorted because of the steady state, because of attaining steady state, and the capacitor is opened. So this is IL, this is IC, which is 0, but VC is there. So IC infinity is 0, IL infinity is how much? Can you tell? And also tell me VC infinity. Calculate IL infinity and VC infinity from this. I'm zooming the circuit and the so this is open, right? So this is 2 amperes. This is 2 ampere. So apply Ohm's law, and this 2 ampere will flow here. And VC infinity is 3 into 2. Yes or no? So 6 volts. 3 into 2. Understood? This drop, right? 3 into 2. So 6 volts. So accordingly, you can determine all the parameters. VL infinity is also 0. Now see the next problem. You need to find the time constants of the circuits. So in order to determine the time constants, because we are doing e to the power minus t by tau, this tau is equivalent time constant of the circuit. Equivalent circuit time constant. So you need to know how to determine equivalent time constant. So it is nothing but R L by R. And these are L equivalent by R equivalent. And if it has capacitors, then it is tau equal to RC. The R equivalent into C equivalent. So C equivalent you calculate and R equivalent you calculate from this. While calculating equivalent resistance, replace the independent sources with their internal impedance. So for the current source, you replace it with open circuit. And hence, for the first one, this is only 10 plus 2, seeing from this node. So R equivalent is 10 plus 2, 12 ohm. But L equivalent or C equivalent for the first circuit in your screen, on your screen is this one. So 6 and 12 are series. So 6 into 12 by 6 plus 12. And then it is in parallel with 2. So parallel capacitors get added. So, and then it will be in series with 3. So first let me do this. 72 by 18 plus 2 is 6, and 6 is in parallel series with 3. So 6 series with 3 means 6 into 3 by 6 plus 3 is 2. So C equivalent is 2, and for the first one, and R equivalent is 12. So time constant is 24. But see, this is micro and this is kilo. Or sorry, this is only ohm. So no issue. So this is micro second. So for the second one, this one, you also determine R equivalent, but now you have a voltage source. So voltage source you short, and then 20K, and then you have 5K, and then you have 2K. But this 2K is not included because you are actually assessing the R equivalent through this node. So 20 parallel 5 will be R equivalent. Is this step clear? Because R equivalent, we need to calculate across about these two nodes. So this is open. You need to open and see. So this is not participating. So 20 into 5 by 25 is 4. So C equivalent, L equivalent calculate. L equivalent you see from this side. So 6 is in parallel with 3. So 3 into 6 by 9 in series with 1. So 3. But milli. And this is milli and this is kilo. So tau for 2 is L by R equivalent. So L equivalent is in milli and R equivalent is in kilo. Okay. 3 and this is 4. Okay. So 0.75 microsecond. Okay. So these are the way you can determine the equivalent time constant. So now do this problem. So this is based on charge conservation, right? I told you, na, whenever the impulsive forcing function is there, because the capacitor was initially maybe having some different charges, and then you are applying different, connecting the two. So it is kind of impulsive. Impulsive forcing function. So better you apply charge conservation. Because here only the voltages are asked. So what is the philosophy? That your total charge before and after remains same. But here there is a dissipating element. So if no dissipating element, right, then you can apply charge conservation. But here there is a dissipating element. So what you can do, equate charge flows till this VC1, I can tell VC2, VC1 equal to VC2. Once VC1 equal to VC2, no charge can flow. Because to the resistor, it appears as a zero voltage. If VC1 and VC2 are same, then plus VC1 minus VC2 equal to 0. If they are equal, plus VC1 minus VC2 minus VR equal to 0. So if this is 0, then VR is 0. And if VR is 0, no IR will flow. So charge only flows till VC1 equal to VC2. So if there is a dissipating element, we can apply kind of charge conservation, but charge is not conserved because of the dissipating element. So we can apply equating the voltages. So what does the equating the voltages at VC1 infinity should be equal to VC2 infinity. And they are only asking us what are VC1 infinity and VC2 infinity. So what you can do? Yes. What I can do? So energy is dissipated in the process of charge combination and recombination. So I can write like this, that before switch was on, what was the charge? Charge was initially 100 volt into Q equal to CV, right? C into this one, 20 micro. But this is minus because this is opposite polarity. So 20 volt into 5 micro. This is the net charge. Net Q before switch on. Now after switch on, what can I write? Let's say the voltages are becoming equal, because I told you they had to be equal to stop the recombination. So they should be equal. So let's name them VC multiplied by C1 plus C2, because that is the equivalent capacitance. So CV1 plus CV2 is the net charge, Q net new charge. So what can I say? At equilibrium, Q or Q net, since I need the voltage, VC infinity into C1 plus C2 should be equal to 100 into 20 micro minus 20 into 5 micro. So VC infinity equal to VC1 infinity equal to VC2 infinity, and this is giving me 100 into 20 micro minus 20 into 5 micro divided by C1 plus C2, which is 25 micro. So how much is it coming? Yes, how much is it coming? See, charge always is conserved, right? So apply charge conservation. But the energy is changing, right? Energy before and after should be changing. Because the voltage across the capacitors are changing. So you can write like this: WC1 0 minus plus WC2 0 minus equal to WC2 0 infinity plus WC1 infinity plus WR. So what I'm trying to tell, W means energy. The energy stored in the system before the switch was on should be equal to energy stored in the system plus energy dissipated by the system. Some part of energy is dissipated. But charge, total charge, what was stored is now gone nowhere, right? It is splitted only. So can you tell me what is happening actually? So charge is recombined, but the voltage is now reducing. So the energy is reducing, but charge never gets created or destroyed. So this charge conservation holds true, always. Always holds true. So that's why we are equating new charge with old charge. Any problem, kindly tell me, okay? Because I cannot understand who is having problem, so you need to speak up. So this gives me how much? 1900 divided by 25, right? So 76 volts I am getting, okay? So I am getting 76 volts. Both are should be equal to 76 volts. Similarly, this is a special case where you need charge conservation. See, always VC 0 minus need not be equal to VC 0 plus. Why? During impulsive forcing function. And what is the situation of an impulsive forcing function? Let's say I connect 20 volt across a previously charged capacitor of 10 volt. Then what will happen? In such cases, KVL will fail. So apply charge conservation principle in such kinds of impulsive situation. This is a kind of impulsive situation. So you need charge conservation. So for example, I solve at t equal to 0 minus. Okay, I'm just showing you a small part and t equal to 0 plus. So what will happen? This is 100 volts. This is 5 kilo ohm. Switch was initially in position 1. So capacitor should be open circuited. And VC0 minus is 100 volts. Capacitor open circuited because it already reached the steady state at position 1. This is 100 volt. Now 100 volt is appearing across the capacitor. Okay. Now once this is in charged position, I shift to 2. So capacitor should be modeled with open. This capacitor, since it was having initial voltage of 100 volts, so I give a strength of 100 volt in series with a short circuit, assuming 0 initial condition, and 0 voltage means short. So short circuit in series with the initial condition of 100 volts, and then it has again 5 microfarad, which was initially not charged. So what will happen? What is VC0? So how can I model a uncharged capacitor also with short? So VC0 plus, if you can see VC0 plus, if I apply KVL, gain, and this is gain equal to 0. So VC0 plus is now becoming minus 100 volts. Yes? Sorry, I'm doing opposite things. VC0 plus is not minus 100, right? You are not giving attention. VC0 plus is 0, right? One second. Yes. So VC0 plus is what? Yes? I want to hear some answers. Yes, none of you are answering. So how to model at 0 plus? Kindly tell me. Let me draw in a fresh page. Yes, how to model this circuit at t equal to 0 plus? So VC, up to this we know VC1 0 minus is 100 volts and VC2 0 minus is 0 volts. Now I want to ask you how to draw at t equal to 0 plus. So how to model a capacitor with initial charge? It is 100 volts in series with short circuit. But the capacitor voltage across this complete thing should be taken. This is the total model, right? VC total model. So this is still VC 0 plus is still 100 volts, which is okay. But you see, this capacitor was not charged. Now in the 0 plus, it should be modeled with short circuit, right? Because 0 voltage modeled with short circuit. So this is violating KVL. Why? Because you are actually shorting 100 volts. So one side it is 0 volts, another side is 100 volts. So it violates KVL, right? So now you are actually convinced you should apply charge conservation here. Because in this kind of scenario, the voltage across capacitor will no longer be 100 volt after the switching. As soon as you switch the switch, as soon as the switch is turned on, this voltage will no longer be 100 volts because charge splitting will take place based on the law of charge conservation. So charge splitting will now declare VCs. And how much will be this? Based on the strength of the capacitor. So we know that, so use charge conservation as KVL fails. Okay, the KVL fails, it is okay. So now you see this is 100 volts initially and the switch is on, but the strength is 20 microfarad and the 5 microfarad capacitor is here, which is uncharged to 0 volts. This is the situation at t equal to 0 minus. Now I turn on the switch. How the charge will split? Charge will split, but the voltage should be equal at infinity. This is a law. Voltage should be equal. Finally. So I can write C1 into VC1 infinity. What I can write? This you understood, right? VC1 equal to this. So what I can write is Q equal to CV. But charge I need to know, right? So initial, let us determine charge conservation, right? What charge conservation says? Total charge before and after combination should be same. So what I can tell, this is this. So total charge, okay. Total charge is VC1 0 minus into C1 plus VC2 0 minus into C2. This is the total charge before. So should be equal to charge after. So what is charge after? C1 into VC1 infinity plus C2 into VC2 infinity. This is charge final. So both should be equal, right? But VC1 infinity and VC2 infinity, we already know 0 volt and 100 volt. So let's determine initial charge using this. So 100 into 20 micro plus 0 into 5 micro. Should be equal to C1 is 20 micro into VC1, but VC1 and VC2 are same. So let us do VC1 C1 plus C2, okay, into V. Let us name the unknown as V. So 100 into 20 micro divided by 25 micro is new V. So V is 80. So after splitting, the charge is coming V final equal to VC1 infinity equal to VC2 infinity equal to 80 volts. So here you see KVL and all those techniques don't work. You need to determine VC0 plus or VC20 plus, but that method KVL was not telling the correct one because KVL was not working there. So that model fails. So here you need to use the charge balance. Okay. Charge conservation only use when the KVL fails. Okay. This was the, and one simple problem, current through the inductor. So current through the inductor, you know, because VL equal to DIL dt. So current through the inductor into L is 1 by L integral VL dt minus infinity to t. Yeah, I already told you. So if you plug in here, I'll just give you the, because voltage you are applying as 2 e to the power minus 3t into dt into 1 by L, which is 100 milli, integration minus infinity to t. You just solve this minus infinity to 0 and 0 to t like that you do, or you break it down, because you already know this is minus 1 minus 0.5. So I can write I of minus 0.5 plus, again I knew the current, minus 0.5 to t into 2 e to the power minus 3t dt. Because current is actually this much, initial current. So you can get the answer, I will write it for you. Okay. Minus 20 by 3 e to the power minus 3t plus 30.9. So why I added I 0.5 and this? Just the initial condition model, that the current source and then you have the inductor in parallel with it. So the inductor current from 0 initial condition and the previous inductor current 0.5 minus 0.5 onwards, both should merge up to find the total inductor current. So because, but also you can see from this integration formula that minus infinity to minus 0.5 and minus 0.5 to t. So both are adding. You can split, and this value you know to be 1 ampere. So just put it and you will get a DC part from here. So you merge it and you will get this one. Okay. Yes, I think it is okay. Yes, you can leave. Okay. We can end the session here. This was the last problem. Okay. Thank you. We can close the session. And next class is on 11th. Okay. Because we already put the session today. So the next class will be on 11th of Feb. Okay. Thank you.